Actually, the official definition is a rectangular array having numbers in it organized into rows and columns. There are many different kind of matrices used for lots of different things in the world of mathematics. We could have a matrix having a single row of numbers in it. Like in the first example, my matrix equals 1, 10, and 12. This would be a 1 by 3 matrix, as it has one row and 3 columns. The mathematical term for these one-dimensional matrices is vector. Or we could have a 2 by 2 matrix. For example, the 1 by 3 matrix, or vector, could be used to represent the position of our object in the scene. It is made of 3 numbers, one for x, y, and z. In trigonometry dealing with 3D space, it's quite common to use vectors to handle this kind of data. This isn't just because vectors look organized, but also because of the beauty of vector and matrix mathematics. The way the matrix and vector operations like addition or multiplication were defined, common but complex sounding actions become super easy. Now, bigger matrices are capable of holding more information, like position, rotation, scale, all in one. These are called the transformation matrices. In 3ds Max, these transformation matrices are 4 by 3 matrices. Now, an example of this really easy transformation that we can do with just simple multiplications of vectors and matrices was what we did to the vertex position in our example. If we have a vector value like the position, we can transform that value into a different coordinate system by multiplying it by a matrix that has the appropriate transformation in it. In our case, this was the transformation matrix of our plane object. This might sound scary, but don't worry about it. There really isn't anything to be afraid of. Going back to 3ds Max, if you just select the plane, I have it selected here, and get its transformation matrix using the dot transform property and evaluate the line, it indeed returns a transformation matrix. It's a 4 by 3 matrix and all the rows are printed separately. 1, 0, 0 in the first row, 0, 1, 0 in the second one, 0, 0, 1 in the third one, and that's actually the position of the given object in the fourth row. So, as I mentioned before, this is called the transformation matrix. That holds not only the positional offset, but rotation and scale applied to the object as well. So, let's get back to our original script and what we did here. So at first we took the local space position of the first vertice of the mesh, and then by multiplying it with the transformation matrix of the selected object, the same object that we took the vertex from, we actually transformed that position into the world space coordinates. So now we modified slightly this script to actually use the first vertice's position correctly transformed into the world space. Let's try it if it works. Save the script, then evaluate it to reinstall this new version. I'll minimize the script. Then try it by clicking on the button. There you go, it looks like it's actually putting it in the right position, but try it by moving around this plane and keep clicking on the icon of our script. You can actually rotate it as well, because as I mentioned, by multiplying with the transformation matrix, we actually take all transformations into consideration: rotation, scale, and movement. So we could actually scale the object as well. It would work correctly. It's putting the tree to the first vertice's position in this transformed space.